Good morning, everyone. Welcome back. Okay, great. Good morning and welcome back. The first talk for today is by Martin Ulirsch from Goethe Universität in Germany, and he will talk about vector bundles on Riemann surfaces and metric graphs. Over to you, Martin.
Yeah, thank you very much for inviting me, and thanks for having me here. I apologize that I could not make it in person. Having a long trip but on relatively short notice is unfortunately difficult during the semester. So I apologize for being only there virtually, but I will get started now. So the topic of my talk is, a bit of a survey style thing, in the sense that it's about the general topic of what should be a vector bundle on a metric graph / a tropical curve. And this whole thing is based on joint work with Andreas Gross and Ulirsch that we just uploaded on the archive 2 weeks ago or 3. And at the end, I will also mention some ongoing work with Margarita Melos and Molcho, Filippo Viviani, and Jonathan Weiss, if time allows for it. Okay, let's get started. There are many ways to think about tropical geometry, and one way to do so is to think about it as starting with an analogy. And the analogy is the analogy between a compact Riemann surface, X, or if you're more algebraically minded, also a smooth projective curve over the complex numbers. Both of these things are equivalent, that's fine. And on the one side, and on the other side, a compact metric graph. So what's a compact metric graph? It's essentially a compact metric space that locally looks like a star thing that is sort of essentially a graph with some edges coming out of it. And another way to phrase it is to just take a finite graph, associate to each of the edges a length, and then build a metric space out of it. And that's 2 different ways of thinking about a compact metric graph. And I mean, usually we assume that this graph is connected, the same way we assume that Riemann surfaces are connected. And we are a bit, we will not always assume that things are compact, the same way we will not always assume that Riemann surfaces are compact sometimes. But okay. But the main point is that for these 2 objects, there is a lot of similarity, and the longer you dig, the more similarities you find. And the place I would like to focus on now is one of the starting points of what you do as a geometer. Namely, you start about thinking about functions on your object, on whatever geometric objects you are studying. And on a compact Riemann surface, you could first think that you want to look at holomorphic functions, but after some thought, you will realize all of those are constant. So really, the interesting type of functions on the Riemann surface are the meromorphic functions. And if you are more algebraically inclined, those are the same thing as the rational functions. And you want to have a similar type of function on a compact metric graph. And those, as it turns out, are exactly the continuous functions from the graph, thought of as a metric space, to the real numbers, such that whenever you restrict it to one of these edges, you can think of it as a piecewise linear function, meaning that, or like also piecewise affine function is sometimes used for that. And the slopes that can show up are exactly integers in Z. And that's what sort of this thing here is supposed to be. And what you should think of is the following picture. You have your metric graph gamma down here, and you have a, here the graph of a function that is constant to some value, constant to some value, and constant to some value here. And then in between, for example, you have like a slope, -1 from left to right, and slope +1 from left to right here. And I mean, it's this type of objects that you want to consider your natural notion of a function on a metric graph. Okay? And whenever you have functions, and I mean, that's true on a compact Riemann surface, and both as well as on a compact metric graph, you actually have too many functions. So the way to solve this in both cases is to introduce a theory of divisors that lets you restrict the type of functions that you want to consider. So what do you do? Well, divisors are formal sums of points on your Riemann surface. And on a metric graph, they are exactly the same thing, formal sums of points on your metric graph. And did I not write this? Okay. Then you can need a way for functions to talk to divisors. That's the divisor map that takes a rational function and sends it to a divisor. And formally, you do it by just saying, well, you take the sum over all points and take the order of the function at this point. And for a meromorphic function, that's just the order. I mean, it's sort of the smallest exponent that shows up in its Laurent expansion. So that's okay. And in the case of a metric graph, the thing you want to say is something slightly different. Namely, it should be the sum of the outgoing slopes at P. And that should be your order of the function at this particular point. And you might wonder, can you also take the sum of the ingoing slopes? And the answer is yes, but then the whole theory just has a few minus signs in it. So, I mean, that's just a choice you need to make. And okay, you can then check that this behaves reasonably well with respect to addition and all. And once you know that, you can define the so-called Picard group, which is just given by identifying two divisors if they are different from each other just by the principal divisor, meaning a divisor of the form divisor of f for some rational function. And that you can just formally do for x. And the same way you can do formally for a metric graph. So that sort of is that type of analogy. And I mean, the first question you might ask, okay, is why would you even define it that way? I mean, there's of course the a posteriori reason to do so. Namely, you will see that this gives you a rich theory, which I will convince you will give you an even richer theory if we go towards vector bundles. But there's still a little bit of a question: is there a connection between the two? Is there something more that motivates this? And I sort of want to lose a few words on that connection before continuing. So the setup to think about this is the following. You have a non-Archimedean field, which for simplicity we assume to be algebraically closed. And if you're worried about these things, you can also assume that the residue field is the complex numbers and not something in characteristic P in particular. And well, R should be its valuation ring. We start with a smooth projective curve over the generic fiber of this, meaning over K, and we choose a semi-stable model. So what you should think of is that this is some form of family of curves where in the generic fiber, you have the smooth projective curve you started with. And in the special fiber, you end up getting some form of nodal curve or semi-stable curve that you want. And you want this whole thing to be flat and proper and have all kinds of nice algebraic geometric properties, but you don't want it regular in particular. Okay, so that's the setup we want to look at. And building on this setup, we can construct the so-called dual metric graph, or also sometimes known as the as the non-Archimedean skeleton for those people who know. And that is given just by taking the dual graph of the special fiber, meaning you take a vertex for each of the components here. So here you have these 7 vertices that correspond to the 7 components. And you connect 2 of these vertices whenever there is a node connecting those 2 components. And well, then if you look a bit more carefully, you also will see that, well, locally in the model, oh, sorry, I shouldn't have done that. Let's go back. Locally in the model, you will see that there is, let's just get rid of this, it's dangerous. Yeah, you will see that the equation in the whole family is given as x times y equals r, where r is an element in the valuation ring. And then then you take the valuation of r as your edge length here, and that also does not just produce some finite graph. So it also tells you about the metric on that graph. And I mean, it really comes sort of from the fact that you're not just looking at this nodal curve, but the whole family of the curve. Okay, so now what does this have to do with divisors? You start with line bundle on the on X on the generic fiber. And if you are willing to be on the safe side, you might want to assume that this X here is regular for the argument that I'm going to make to work. You can do it more generally too, but you have to say different words that I don't want to say. Then since it's regular, you can find an extension L to the whole Picard group of the family. And then what you do is you consider in particular, then you have a line bundle on the special fiber. And this means you can take the multi-degree of that line bundle, meaning you restrict the line bundle on each of the components and take the degree of said line bundle. And that will produce you a divisor on the metric dual graph. Okay, now there's some ambiguity in this definition. Namely, you could take a different extension, because the sort of the universal relative Jacobian is not separated. So you have different limits in this context, and you could take one of these and you can end up getting a different multi-degree, and those two are in general not the same. Okay. But what happens can be, in order to understand what happens, we can assume that we sort of are in a special situation, namely if L prime is given by L, twisted by one of the components that we call di, for example, this one here, then we know that the degree of the L prime, as it restricted to dj, some other component, is given by the original degree of L plus the number of nodes that intersect di in dj, if I is unequal to j. And in order to keep the total degree constant, then this has to be equal to the degree of L restricted to di minus the valence of vi if I is equal to j. So in a certain way, this is this sort of produces for you a piecewise linear map, or like a rational map on the metric graph as follows. What we observe is that the multi-degree is the of L prime, which is a divisor, is the same thing as the multi-degree of L plus the divisor of a function f, where f of vj is equal to 1 if j is equal to 1, and 0 if j is unequal to 0. So so what happens? You look at this particular piecewise linear function, and at the point I, you end up taking the order, and then you take sort of the order is you have like a slope -1, outgoing slope -1 at the point vi, and you look at you take the sum of the outgoing slopes, and that is exactly minus the valence, which corresponds to this thing over here. And at all other points, it's either just constant equal to 0, or you have maybe a few edges that connect to vi, and those all have slope, outgoing slope 1. So you end up getting 1 for each of the nodes which that intersect di, and that's exactly what's encoded here. And now I'm making the vague claim that if you now iterate this type of construction there with the di's here, and just twist with different types of components, and are also willing to twist with components in suitable blow-ups of your family, then you end up getting a notion that recovers exactly the sort of this linear equivalent symmetric graphs that I talked about earlier. Okay, are there questions at this point before I want to take the next step and talk about something newer?
Any questions?
So this is basically chip firing, right? Because the audience—
This is exactly chip firing, yes.
I've seen this quite a few times.
You have seen this a lot, and many people have seen this before. And some people might have also seen this when they study compactified Jacobians. And this is a very classical story. I just tried to sort of set up the thing to get towards vector bundle, which will be a generalization thereof.
Yeah, exactly. Yeah, thank you. Thank you.
Are there questions then?
At the moment, I
Not,
don't
then-
see any hands raised. So.
Okay, then I will just continue. And sort of the question that I want to ask now is that, well, we all know that sort of well, divisors up to linear equivalence, they are the same as line bundles up to isomorphism. So then sort of classically the way to generalize line bundles is to think about vector bundles, which somehow allows you to take values not in C, but in more than the sort of then in more, but in more than just one entry. And I mean, that's sort of the basic question that I want to ask and also give at least one answer to today. Okay. And in order to understand how this works, we further our analogy, and in particular, we continue with some technical parts that first of all tell us what a line bundle on a metric graph is, and this is due to Mikhalkin and Zharkov. And then we will generalize it from there. So sort of to spin our analogy between Riemann surfaces and metric graphs further, we have meromorphic functions on X, of course, and we can also not just think of it as global functions, but also take a sheaf of such functions. And instead of just like global rational functions on our metric graph, we can also take the sheaf of continuous piecewise zlinear functions on gamma. And inside of this OX of MX is, here is also OX, but OX is unfortunately not such a great object on the tropical side. But there's also OX star, the sheaf of invertible holomorphic functions on X. And there is an analog onto that sheaf, and it's the sheaf of harmonic functions on gamma. So what does it mean for such a piecewise linear function to be harmonic? So if U is some open subset of gamma, and we take an F, then this thing is called harmonic if the divisor of F at the point P is 0 for all P in U. Meaning, in other words, that the outgoing slopes at each of the points, if you sum them up, they're all equal to 0. So this in particular means if you look at an edge and you have only two if you're in the middle of an edge and you have like a point of valence 2, then you have only two outgoing slopes. And I mean, and this just means the two slopes have to be, I mean, the one to the right, for example, is positive, then the one to the left has to be negative, and they have to have the same, to be the same absolute value. So what this means is that on an edge, this type of harmonic function is linear. And if you are looking at vertices of valence higher than 2, then you end up getting something that is a bit more interesting, but you still have this linear condition that the sort of the sums of the vertices have to be equal to 0. Maybe just a tidbit for the experts. Technically, in order to be harmonic, you use some form of Laplace operator, and that is usually defined as minus the divisor of F. But for our purposes, this is the same thing here. Okay, so we have now a notion of OX star on our metric graph. And then, of course, one could say, okay, why is it analogous? And the point is that sort of you can think about line bundles on X as OX star torsors, and then use, and I mean, this is a well-known connection between the two things. And I mean, they're up to isomorphism, the same thing. And then you can just define line bundles on your metric graph as H gamma torsors on gamma. And sort of the theme that I want to sort of communicate here is also that sort of directly defining line bundles, although Mikhalkin and Zharkov managed to do it, can be problematic in tropical geometry, to say the least. But thinking about torsors over suitable sheaves of groups is less problematic. So our perspective is strictly the perspective of looking at like principal bundles on X rather than on vector bundles as an inherent object. So and I mean, as I said, well, we can just use these this H gamma torsors and define them to be our line bundles on gamma. Okay, now why is this? I mean, maybe I should then just repeat something very classical that all of you have seen in your first class where you talked about sheaf cohomology. And then I want to do the same argument also on the metric graph. So we have a short exact sequence from OX star to MX to the quotient sheaf MX mod OX star. And this induces a long exact sequence as follows from C star. That's the global sections here, global sections here, global sections here. That's this one and this. And now you can do some standard identifications that say, well, this thing here is the same thing as the meromorphic functions on X. This thing is nothing but the divisors on X. And this map that you have, the induced one is the divisor map. And then you end up seeing that, I mean, the H1 here ends up being 0 because, well, the sheaf here that you want to look at, this MX, has way too many functions. So H1 is 0. And now you're in the situation that H1 of OX star, which by some straightforward check cohomology argument classifies OX star torsos, that is line bundles on X, is now the same thing as the Picard group, which we defined as divisors modulo div of RAD, so meaning modulo principal divisors. So that's sort of the classical argument that you all know from whichever context you learn sheaf cohomology in. And the same type of argument also works on a metric graph. So here we have a short exact sequence from H gamma, the harmonic functions, into the piecewise linear functions, and then to the quotient. You write down what this means. Then global harmonic functions are constant. It's an easy exercise to see. Here you end up getting the rational functions on gamma. Here you end up getting something that you, if you think about it for a little bit, will turn out to be the same thing as divisors on gamma. And the map here is also the divisor map. And by the same reasoning, we can conclude that H1, namely of H gamma, namely the set of torsors over the harmonic sheaf of harmonic functions, is in fact the same thing as the Picard group of gamma. Okay, so what I just recall to you is the standard way of identifying divisors modulo linear equivalents with line bundles up to isomorphism. And that sort of explains why this type of sheaf, the sheaf of harmonic functions, is actually a central object on a metric graph because it functions as the right analogon of OX star. And we will now use this sheaf together with some other observation to define what could be a good or a first notion of a vector bundle on a metric graph. Are there questions about this recalling of things?
So in each case, you're just taking the global sections functor and then taking the long exact sequence.
Exactly.
Yes. Thank you.
Okay. So our strategy will be that we want to not now to define vector bundles. We do not want to look just at OX star torsors, but at GLN of O torsors. So we need to have a notion of a general linear group in tropical geometry. And the first way of doing that is as follows. We can think about, well, the tropical numbers with I mean, R unit infinity with the min and the plus as the addition and the plus as the multiplication. And in this language, we can just naively define what is the GLN of over the tropical numbers. And well, it's the n cross n matrices for which there exists a B in another n cross n matrix such that A times B equal B times A is the identity matrix. Watch out, in our tropical logic, the identity matrix is, well, it has zeros on the diagonal and infinity away from the diagonal, simply because the zero element, zero is really 1 in tropical geometry and infinity is 0. Okay, and now, and now we see that this, now we have to observe that this is actually a very restrictive definition. In fact, it turns out that this is the same thing as considering all the matrices such that there is a non-infinity, there is exactly one non-infinity entry for each row and each column. So in a way, it's some form of generalizations of a permutation matrix in the tropical realm that also allows sort of some scalar value in the entry where it's non-infinity/0. And it's exactly this observation that lets us say the following, namely this group GLNT, so the general linear group over the tropical numbers, is isomorphic to the symmetric group because of permutation matrices, semi-direct product with the additive group R to the n, meaning that you do a permutation matrix, and at the non-zero entries, you are allowed to add some form of real number to it. And that's exactly another way of describing this semi-direct product. And before I continue, I want to just say 2 words for the experts in the audience. Notice that this Sn is the same thing as the Weil group of GLN, and the Rn is generated by the co-character lattice of the maximal torus, the diagonal maximal torus GM to the n in GLN. And I'm saying these words because if you happen to know what these words mean, then you immediately can think, oh, this is not just for vector bundles, this is really for all principal bundles, what we're doing here. But if you don't know, please ignore whatever I just wrote in red. And now that we have sort of our general linear group, and we know that this has a very specific and relatively easy shape, then we can just say, okay, a line bundle is an H torsor. Now we want to plug in H into with values in our GLN. So what do? We take a vector bundle of rank n on gamma to be an Sn semi-direct product H gamma to the n torsor. That's sort of the new definition that we are proposing. And it seems relatively natural just from the analogy that I gave to you. But of course, now I have to convince you that this also gives rise to an interesting theory. Before I do so, are there questions about this?
Yeah, there's a question.
So if instead of min, I take max, so can I define GLN in a similar way for that as well?
Oh, yeah, you totally can. I mean, then you would, whatever there is infinity, there would be a minus infinity, and everything will work out the same way.
All right, all right.
And I mean, okay, and then there will be sort of a sign flip here in this isomorphism. I mean,
so I have one more question. This is generated by cochain. What have you?
Oh, sorry. This was written in a poor way. Let me read it out again. Generated by the co-character lattice of the diagonal maximal torus in GLN.
So is it Rn star R star power n or Rn?
It's Rn actually, because you exponentiate here, meaning that the co-character lattice, that's Z to the n, and it's just the Z to the n tensor R.
Okay. Okay.
So I mean, so the multiplication that is happening in Gm to the n of k, say, will be under tropicalization turned into addition on R. So sort of the multiplicative structure turns into this additive structure, which you can think of the additive structure of the exponents, if you like.
Okay.
Does this answer the question?
Yeah. So yeah, the exponential map is acting in between, which converts from R plus to R. Is that what you're saying?
I'm not. I didn't hear the full question actually. Sorry.
So you said that there is an exponential map which is there in between.
Yes, I mean you can think of the exponential map from C star to R. That well, I mean, it takes the exponent of a let me say it's not exponential. It's sort of minus log absolute value from C star to R. And
okay.
If you do this over a non-Archimedean field with respect to some non-Archimedean norm, you are in the situation that you can easily tropicalize, but you can think of it as some form of limit of this minus log absolute value on C star, the complex numbers to the star.
Okay, thank you.
Okay.
I have a question. Just a quick question. So is the appearance of Sn here related in any way to the fact that if I work over F1, then vector spaces are
this is
finite?
exactly related to that. Yes. A third perspective on what I just did could also be that you can think of what is the incarnation of GLN over the field F1 with one element, that's Sn. Then you take the base change of this to the tropical numbers, and that adds the R to the N here.
Great, thank you.
And I mean, this can be made precise, by the way. There is a very interesting article by Oliver Lorscheid, where he really sets up a framework that allows you to take base changes of Y groups and everything. And quite literally over F1, if you take it, you get Sn, and then you take the base change to tropical numbers, it's this one. So what I just said is not just an analogy. This is like based on a solid type of math in this, the second blueprint article by Oliver Lorscheid, if that is of interest to people.
I see, thank you.
Okay, okay, so this is a vector bundle. So the first question one could ask is, how should we think of these objects? And well, one way to think about it is the following. And I mean, this is maybe the first way one can come up with. It's the if you have vector bundles up to isomorphism, this thing should be in a natural bijection with the non-abelian cohomology H1 of on gamma of Sn, semi-direct product Hn gamma. And I mean, this is again the same argument that you also do with non-abelian first check cohomology that shows you that H1 of X of GLN is just is GLN to us, and here it just works the same way. And this in particular tells you that you can think of your vector bundles in terms of its transition maps on a nice cover. And on a metric graph, you have a best possible cover, namely one where each of the open subsets is just a star around the vertex. And from there, you can define all the basic operations that you can usually, as usual, also define on transition maps. For example, you can define what is the direct sum of two vector bundles, what is the tensor product of two vector bundles. Sorry, this was poor handwriting. And you can define what is the dual of a vector bundle, what is the determinant of a vector bundle. You can define pullbacks along I mean, we have already defined it along. I mean, I guess pullback should work along all continuous maps of metric graphs. Push forwards are a bit more tricky. For this, you need that that it's actually a covering space map. But I mean, once you have that, you can define all these things in terms of the transition functions, which works essentially the same way as it does in the classical case. And I just want to say this is all possible. With one exception, I mean, in principle, you can now also define a bundle of homomorphisms from E to F. But since our perspective is that of principal bundles, well, homomorphisms of principal bundles are either they don't exist or they are isomorphisms. So sort of we don't, I mean, we could in principle define a bundle hom from E to F as E star tensor F, but I don't think we should, because sort of the bundle of homomorphisms between two vector bundles should in some sense recover linear maps if we're working over just a one-point space. And well, linear maps in tropical geometry is a whole other story that is much more intricate that we are comfortable proposing. So we explicitly exclude sort of the hom bundle just because we are in the perspective of principal bundles, and there you cannot really write this down as easily. Okay, so that's one way to think about it. So that's nice, and it is exactly how it works in the classical world. And then there's another way to think about it, and that is one that is particular to this situation, to the metric graph situation, and which also allows us to really prove new results about this. And that is the perspective of multidivisors. So suppose we have a topological cover of degree n of our metric graph F. And let D be a divisor on the covering space gamma tilde. And when we think about topological covers, we also want to think of this as being an isometry. so that it is actually classified by the fundamental group of gamma and so on. And once we have a divisor on gamma tilde, we can apply what we learned, namely this here. We take the associated line bundle to this divisor and then push it forward along F. And this type of thing is then a vector bundle of rank n on gamma, meaning the n that is in the covering space degree turns out to give you the rank of the vector bundle on gamma. Another word for the expert, this has nothing to do with the Bacon-Noreen rank. Okay, and the central proposition is now that, I mean, this construction as it is here could have worked in algebraic geometry or classical world, Riemann surfaces and so on as well. But the central point is that on a metric graph, these are all the vector bundles, meaning that vector bundles of rank n on gamma up to isomorphism are the same thing as tuples or consisting of a cover of rank n, degree n cover, a divisor on the covering curve gamma tilde, as this whole thing up to linear equivalence of the D and up to isomorphism of the cover. So meaning for every, we can sort of study our vector bundles on the metric graphs by looking at covers and divisors on the covering curve. And this is exactly the type of perspective that allows us to sort of prove our central results that I'm just going to go through now. The first one is an analog of the classical Birkhoff-Grothendieck theorem, meaning on a projective space, every vector bundle is a direct sum of line bundles. And in our framework, this holds true as well. If gamma is a metric tree, then every vector bundle on gamma is a direct sum of line bundles. Turns out to work simply because, well, covering spaces of a tree are already disconnected and
is a bit unstable, so we missed.
I'm sorry?
Martin?
Yes, hello? Was there an interruption?
Can you hear me?
I can hear you, yes.
Yeah, I think your internet was unstable for a moment, I think. So we missed
okay.
a
Sorry.
couple of sentences.
Where did the instability occur at the proposition?
Sorry?
When did it start? When I started
about 3 sentences before, like when you started talking about the Birkhoff-Grothendieck theorem.
Okay. So let me just repeat what I said there. So the classical Birkhoff-Grothendieck theorem tells you that if you have a holomorphic or algebraic vector bundle on the projective line, then it is a direct sum of line bundles. And in our framework, the same is true. If you have the gamma metric graph to be a tree, then every vector bundle is a direct sum of line bundles on this gamma. And the main reason for this comes from this proposition, meaning in order to describe, well, you need to describe covers of a tree, but covers of a tree are already disconnected. So being disconnected means you get a direct sum. Similarly, we also have a classification of vector bundles on the tropical analog of an elliptic curve. Namely, if gamma is a metric cycle, then we can show that indecomposable vector bundles of rank n and degree d on gamma, this thing here, indecomposable means you cannot write it as further direct sums. And I mean, degree you have to define as the degree of the determinant and so on. This type of set is in a natural bijection with gamma. And this is sort of generalizes the classical result of Ayyer, which says that on an elliptic curve, indecomposable vector bundles of rank n and degree d are in a natural one-to-one correspondence with the points of the elliptic curve. So the same is also true on the tropical incarnation of elliptic curve, namely on a cycle. And another thing that could be interesting is the notion of a Riemann-Roch theorem or the wild Riemann-Roch theorem, meaning that it's generalization to vector bundles. And what does it say? If you have a vector bundle of rank n on your metric graph, then now this is the Bacon-Noreen rank, which you define by taking the Bacon-Noreen rank on the cover in a smart way. And so you take the rank of this vector bundle minus the rank of the dual vector bundle tensor with the with the line bundle associated to the canonical divisor. And this thing is then the same as the degree of the line bundle, of the vector bundle, minus n, that's the rank of the vector bundle, not the Bacon-Riemann, the rank of as a vector bundle, times the genus of the metric graph minus 1, and the genus of a metric graph is its first Betti number, so the number of holes in the metric graph. Please note for that this is that here there is not, this is sort of a version of the Riemann-Roch theorem for vector bundles that do not involve any terms like H1 terms, meaning first homology terms, just because we don't have these things on the tropical world. So we sort of have to, in order, so this statement is nevertheless also true on a compact Riemann surface. You just have to apply the Riemann, I mean, I guess, a nice formal derivation could be just by using the Hirzebruch-Riemann-Roch theorem, plugging in what's there and applying Z duality to avoid having to work with cohomology groups. Okay, and the last result I want to say is that in this perspective, we can also prove a tropical analog of the Narasimhan-Seshadri correspondence that says that, in our case, it says that semi-stable vector bundles of degree 0 on our metric graph are the same thing as vector bundles with locally constant transition maps, and which is a statement that's also true in the on a compact Riemann surface, and that's the classical Narasimhan-Seshadri correspondence. There they also talk about representations of the fundamental group, but that turns out to be, well, true, but not canonically true in the on the metric graph world. That's why we don't want to say that. Okay, so what this result should illustrate is that sort of several of the classical results about vector bundles on compact Riemann surfaces are also true in our new proposed framework, and that sort of suggests that this is at least a rich theory. For now, these are all just purely combinatorial results that are inspired by something algebraic, but the question one can now ask is, what does this have to do with the with vector bundles on algebraic curves or compact Riemann surfaces? Before I go into this, are there questions about these results?
Questions? I have a couple of questions. So this notion of semi-stability, how do you define it? Is it
as slope semi-stability? So you can define a notion of subbundles in terms of transition maps. And I mean the rank, you know, because you know the size of the transition maps, and you you need the degree to define its slope, and the degree is given, well, you take the determinant in terms of the transition maps, gives you a line bundle. Line bundles are the same thing as divisors up to linear equivalence, and for divisors, you know what the degree is. It's just take the sum of all the coefficients of points. So you have a notion of degree, you have a notion of rank. So you can define the slope, and then you define semi-stable things to be exactly those vector bundles, such that for all subbundles you have the slope inequality, meaning slope of the subbundle is less than equal to slope of the whole bundle. And so it's exactly the same thing you do in algebraic geometry.
Algebraic geometry, right? Yeah. So what kind of a category do these vector bundles form?
Yeah, this is a good question, and the answer is really they do not form a good category as vector bundles. They form a category as principal GLN bundles. So if you think about it, principal GLN bundles on X, they form a category, but all the morphisms there are isomorphisms, and the same thing is true here as well. And in particular, we do not define the notion of a homomorphism between two vector bundles. And the reason is that I think it's fair to say that even the notion of a linear map between two tropical linear spaces, or even three tropical linear spaces, is not well understood. So we are far away from understanding that. So we should not give a definition in the more general situation of vector bundles. And therefore we do not say what a homomorphism of vector bundles actually is, and simply because I personally don't think there's a final answer to the question what is a homomorphism of tropical modules. I mean, I guess of like tropical linear spaces, and I think that should be that should be solved first, or at least given a convincing answer first before we can make any statements along these lines here. So we are thinking about our objects in terms of principal bundles, and there all the morphisms are isomorphisms. And isomorphisms means they have the same transition maps.
I see. So that perspective in terms of F1 geometry, wouldn't that suggest a notion of morphisms? Because over F1, you have a category.
Yes, it would, but we are not so happy with it. I mean, it's a very restrictive notion. It somehow generalizes permutation matrices and entries within the tropical numbers. And
I see.
It's okay. It's certainly a working notion. And I mean, if you want this to be the right definition, then you can define, for example, a homomorphism bundle, and it's isomorphic to dual bundle, tensor, the target bundle, and so on. I mean, these things work. It's just, well, I guess we are just not happy with it as a general concept. I mean, we're happy with this being the type of isomorphism. That's okay. But homomorphisms, I mean, it makes too many suggestions that might not be true in the end. So, I mean, I guess we're just refusing to call it that. That might be the right term. Yeah.
And just one or two more questions. So, is there an analog of Higgs bundles? And
yeah, we wrote something down. In hindsight, we shouldn't have written it down because we have now thought a little bit about sort of the connection to non-Archimedean things. And sort of the non-Archimedean Higgs bundles that show up in, well, I mean, this might be clearer of the next result, but if you tropicalize sort of these non-Archimedean Higgs bundles on an elliptic curve, it seems like there is that sort of in its most naive way, the Higgs field completely vanishes under tropicalization.
I see.
That being said, I will come back to what you just asked after I talked about the next result, because there is something more that you can say. It's just sort of the first naive approach seems to suggest that when you tropicalize, the Higgs field becomes zero.
I see. Thank you. There's a question in the chat which says, could you please repeat the definition of a subbundle?
Oh, yes, very much so. Write your vector bundle in terms of its transition maps. And then a subbundle is given by you have a subbundle of this if there is like a sub-transition map, so to say, meaning that each of the transition maps has like a block diagonal form, and you take one of those in a consistent manner, you take one of those blocks, and that's the subbundle. Does this answer your question?
Jyoti?
Oh, great. Okay.
So what is the linear equivalence in this setting, in the metric graph setting?
Oh, sorry, the linear equivalence is just, between divisors is given by taking divisors of a piecewise linear function.
Okay. Thanks.
Or chip firing if you are more combinatorially minded. Okay, let me maybe now start talking about the connection to algebraic geometry. And so then I can lose a few more words on the Higgs bundle question, actually. Let's talk about the process of tropicalization. And as it turns out, it works best in the case of a Tate curve. It also works in genus 0, genus 1. And for genus 2, well, there are problems. But I mean, people who know about vector bundles in the audience know that the fact that the fundamental group will be non-abelian will cause problems anyway. Okay. So let's think about this. We have the setup as above. Now X itself, though, is a Tate curve, meaning it's given as like GM up modulo Z essentially, and then gamma X is the dual metric graph, which is just a cycle of length devaluation of this Q that shows up. And we want to now define a tropicalization map from the moduli space of semi-stable vector bundles of rank n and degree d on this elliptic curve. And here I'm writing AN because this is, you have to sort of take the non-Archimedean identification for this to be the right thing, but you can think of this as being k-valued points, if you like. And it should be a map from these k-value points to the moduli space of semi-stable degree d, rank n vector bundles on gamma X. And what happens now is that we take such an element here, which up to base change issues is the same thing as a vector bundle on a semi-stable vector bundle on elliptic curve. And we know a lot about semi-stable vector bundles on an elliptic curve, and there are results by Ayyer and Oder that we can massage a little, and it tells us that this thing is S equivalent, meaning that they have the same Jordan-Hölder filtration, to the direct sum of E1 up to EH of vector bundles, where each of those EIs is indecomposable. And using Ayyer's classification with Oda's work tells you that this EI is then, each of these is a push forward of a line bundle for a line bundle Li in the Picard group on X tilde, where X tilde and pi, where X tilde is sort of the natural cover and pi is the projection, meaning that X tilde is GM not to the Q to the Z, but Q to the N times Z. So it's the natural degree N cover in this state curve world. And sort of the classical algebraic theory already tells us that each of these indecomposable summons is a push forward of a line bundle. So since this is all true, we can now define tropicalization by sending this E to the direct sum I equals 1 to H of the push for the tropicalization of this cover, which is just like the n-fold winding of the cycle. And then you just tropicalize the line bundle, by extending it, taking multi-degrees, and then taking equivalence classes, as I explained in the beginning of this talk. So this gives a well-defined tropicalization map. And the result you can prove about this is that the so-called essential skeleton of this moduli space, so this is a Calabi-Yau variety, so it has like a best possible skeleton. And the skeleton is just sort of a piecewise linear subset of this Berkovich space that arises as a deformation retract in a natural way. And this thing is, I would like to say, isomorphic to the moduli space on the tropical side, but actually you have to be a bit careful. You get only the main component of this, because on the tropical side you get several components, and well, you have to just deal with that. But I mean, you can identify the right component. That thing is now in natural way just the tropicalization of the algebraic moduli space. Okay. Now, this is interesting. It generalizes, for example, also a result by Baker-Rabinov that shows that the tropical Jacobian is the skeleton of the algebraic Jacobian, for example. Okay. A few remarks on this. I mean, I guess technically this theorem also relies on the fact that we're working in equicharacteristic 0, so characteristic P could still be a problem here. And but a few remarks. And this is sort of interesting. That goes towards the question on Higgs bundles. So first and foremost, this is a Calabi-Yau variety, an explicitly given one. So you can think about doing mirror symmetry with these things. And one way to do mirror symmetry is via the SYZ fibration. And this is a non-Archimedean version thereof in the sense of Kontsevich-Seuberman. And this is sort of a non-Archimedean SYZ fibration. Now, there are results that tell us that if we replace this moduli space of semi-stable vector bundles by the moduli space of semi-stable Higgs bundles, sort of the fact that the fundamental group is abelian will then tell us that sort of this moduli space splits as this moduli space times a to the n, I think, or like, I mean, the n-fold symmetric product of A1, for that corresponds to the Higgs field. So the two sort of Higgs field and vector bundle split. And then you can sort of independently look at the skeletons of this moduli space and the Higgs field moduli space, and also get, using our methods, or using, I mean, as a consequence of this theorem, find a non-Archimedean interpretation of the SYZ fibration for the moduli space of semi-stable Higgs bundles on a Tate curve. The way you should think about this is that this is a non-Archimedean incarnation of the Hitchin map, which thanks to the abelianness of the fundamental group is actually very nice and everything splits nicely. And the abelianness of the fundamental group or the non-abelianness in higher genus also prevents us from generalizing such a result to higher genus. So there is much more in higher genus than it happens on an elliptic curve. And so the remark is that we are already working on generalizations of this story. I mean, to other principal bundles like symplectic bundles, orthogonal bundles, and so on. I mean, those types of things are expected to work well and also work well on an elliptic curve. There is also, we also expect lots of a generalization to this story to abelian varieties, where you can also sort of work with homogeneous and semi-homogeneous bundles to get a good version of the story. But our story is pretty clearly not going to generalize to genus 2 or higher, which is kind of a bummer, I admit it. And then, of course, also any types of generalization of the Hitchin vibration in this world to higher genus are also, first of all, much more difficult than what is happening here, but also just not possible because our theory doesn't have that reach yet. So I have like, well, 3 more minutes. Let me maybe just say, maybe just mention one of the problems that show up if you want to generalize it to higher genus. And the central problem in my eyes is the following. Recall, there is the Birkhoff-Grothendieck theorem, which tells us that on a P1, every vector bundle is isomorphic to direct sum of line bundles. That's good, that's great. And now if X is a graph curve, meaning essentially a nodal configuration of pi1s, then the question is, does Birkhoff-Grothendieck theorem still hold? And the answer is yes, only in a very restricted case, namely if X is a chain of P1s, meaning something like this. And that's due to Theodorescu and Martin Stadius. And using that situation, you can also generalize it to a cycle of P1s, which is the special fiber of the Tate curve, just saying. So here it's only almost true, though. So it's not a direct sum per se, but it says that every vector bundle is actually an SN semi-direct product to GM to the n torsor if X is a cycle. So that's also, it's almost the same thing. And if there was no SN, then it would be a sum of line bundles, but here it's that, and it's still combinatorially viable. But what really blew my mind when I learned about this the first time is, as soon as you have in any other situation of graphs, then the Birkhoff-Grothendieck theorem is just false. So it's still true on each component, but you can sort of do a lot of damage by gluing along the nodes, and then this whole story just doesn't work anymore. And this suggests to me that instead of looking at all vector bundles on a graph curve, meaning a nodal configuration of P1s, you should look at a subclass that has better properties. And I propose it to be the following one, namely, we say that that such a vector bundle on E is called locally homogeneous if you take the global, I mean, each of the GM operations on the P1s come together to build a global GM operation on your nodal curve consisting only of P1s. You can form the stack quotient. And I'm saying that a vector bundle on such a graph curve should be called locally homogeneous if it is a pullback of a vector bundle on this quotient stack. And now the good thing is, if you are doing that, then you have a generalization of the Birkhoff-Grothendieck theorem. And I mean, I'm calling it theorem in the making because, well, it's literally in the making, but I'm relatively certain that the statement is actually true, meaning that if you have the X is just a tree of P1s, where also Birkhoff-Grothendieck does not work, but then a vector bundle is then locally homogeneous if and only if it is associated. It's not so simple, but it is associated to a piecewise linear map from the dual graph to the Tietz building of C to the n, meaning that on each edge you choose an apartment of the Tietz building, get a piecewise linear map, And well, if we're in a situation that the dual graph is a chain or a cycle, then you are always in the same building, and then you can read off from this map the multi-degrees of the line or the line bundles that you were considering. But in general, you just need a piecewise linear map to the Tietz building for this to work. And well, there is a generalization of this when X is not a tree, but something with monodromy. And then you can say, well, it's locally homogeneous if and only if you take a B is a bundle of Tietz buildings on the dual graph, and you need to take a piecewise linear section to this bundle. And well, the second part is there's a lot of work hidden still, but I'm fairly confident that this part is true. And as I said, it's a theorem in the making. So please blame me if it's wrong, but it's also not done with any collaborators, so it's really my fault. But anyway, for now, this is all I wanted to say. I'll end here with a hint towards the generalization of this story, which will require a much more complicated object, namely some type of bundle of Tietz buildings or metric graphs. And with that, I hope that also the higher genus case will find it's a good treatment. And I think I'll stop here and open the round for questions. Thanks. I see people applauding, although I cannot hear it.
Sorry?
I see people applauding, so I'm saying thanks.
Yeah. Can you hear us? Yeah. Great. Questions and comments.
I have a question, but I don't know whether it makes sense or not. But the question is that in the case of curves, you have smooth curves of genus G, and you have non-smooth curves, nodal curves. But analogous to that, in the case of graphs, is there a way to distinguish two? Are there two such classes, like smooth graphs and non-smooth graphs kind of thing?
Not really. I mean, the whole story captures exactly the nodal combinatorics. So, I mean, in a way, all of them are non-smooth.
All of them are?
In a way, almost all of them are non-smooth, unless it's just a graph consisting of one vertex.
Oh, okay. Okay.
So, I mean, yeah, I don't know. I mean, I think like it, this would, I mean, there's of course a notion of smoothness for graphs once you want to embed them into some vector space again. But that's not playing any role in the story that I told today.
Okay.
So in the vector space situation, you have they locally look like the Bergman fan of a matroid. But none of these things seem to are playing a role in what I said today. So I don't think I mean, for the purposes of this talk, it's good to think that all these metric graphs are, I mean, all but the trivial ones, so to say, are non-smooth.
Okay, thank you.
Audiovisual team, would you enable the virtual participants to unmute themselves, please? More questions?
Yes, so I have a question. So are there a notion of parabolic bundles?
That's a very good question, actually. And the answer, I think, is a little bit hidden. I mean, first of all, in the tropical theory that I spent most of my talk explaining, the answer is no. But there is something parabolic hidden here. If you look at this type of object, sort of this piecewise linear map from the dual graph to the Brouwer-Tietz building, I mean, it doesn't just encode the vector bundle. It also tells you something about sort of filtrations at each of the nodes coming from both sides. So yes, there should also be some form of parabolic bundles floating around, but since this is a result in the making, I cannot make this precise as of now.
I see. Okay. So is there a notion of ampleness for divisors? Yeah.
I think such a notion exists, but I have to admit I don't know it on the top of my heart, because it essentially means that you can sort of embed your, I mean, using a linear system and embed your curve into some tropical projective space. And that type of thing turns out to not be very closely related to the rank that shows up in the Riemann-Roch and Weil-Riemann-Roch theorem. So somehow the notion that exists in the literature that tells you it's nicely embeddable is sort of not related to the sort of Riemann-Roch type statements, or I mean, well, I mean, there are situations where they are related, okay, but in general, not related to this Riemann rock type statement. So it's sort of a notion that that deserves to be studied, I think, but it's not in a good enough shape to lead to anything yet, I would say. I hope I'm not offending people in the audience.
I see. So like graph curves, what are like graph surfaces, something?
Good question. I don't know. Maybe it's a configuration of P2s or something.
I see.
I mean,
Yeah. Okay.
but I guess you want to have like in a two-dimensional case, you want to have one-dimensional intersections and zero-dimensional intersections. So it shouldn't be a graph curve. It should be a two-dimensional simplicial complex curve, if you like.
I see.
But I have not said much about higher dimensional things just because they get very difficult very quickly as the object to study. The only place where I'm willing to say something is the case of abelian varieties, where you have sort of a good notion of sort of semi-stable degenerations and limits describing those things, namely real tori, and that is also the right tropical analog to do this. But in all other higher dimensional situations, I am not so confident that we have the best notion yet. But then I've talked to people who say, yeah, in the K3 surfaces case, you should also be able to do it, and I'm happy to believe them, but I have not done it.
I see. For rule surface, they are okay. I see. Okay.
So I had a question about the slide with the last slide.
Mm-hmm. That's this one, I guess.
Yeah. Yeah. Could you just comment on how you get a bundle from the map to the Broad-Tits building?
Oh, yes. I mean, what is happening is, I mean, I guess there are two ways to say it, but let me do it the elementary way. If you have like a piecewise linear map, you have like an edge, and on each edge it's you choose an apartment, and I mean, an apartment is more or less the same thing as the co-character lattice of big torus of GLN. And if you have the map, then you sort of on both ends. I guess it should be an integral map, that z-linear map to make this precise. And then you end up having sort of the slope of this map in all of its entries. So this sort of on each edge, this is a map to a copy of R to the or Z to the N actually. And then the difference are sort of and then in each entry you have the difference in the slope. So and this type of slope is telling you that on this component you take a copy of O of that slope, and then you sum them up. And then sort of and then you do this with each of the oh, sorry, no, I said this wrong actually. You have to look at each of the vertices, and at each vertex you get an element in Z to the N, and that element is Z to the N that takes you to I mean it's like a list of n integers, and you sort of build the vector bundle as a direct sum of those O of these integers on that component. And what I just said about the slopes is actually how these vector bundles are glued along a node, and sort of and the fact that it is associated to a sort of to this piecewise linear map to a Tits building means the gluing happens not with an arbitrary element in GLN, but with an element in some torus of in GLN. So it's not something unipotent or whatever. It really is something in a torus of GLN. And this being in a torus, sort of gluing within the torus at each of the nodes is exactly what this locally homogeneous construction encodes, because, well, it tells you that at each node you have like a representation of GM to your vector bundle. This is only possible if it is glued via elements in the torus and not something else. Does this help?
Yeah, it does. Yeah, thank you.
Okay.
And this would work for principal bundles over other groups as well, right? I mean, you could take
I
buildings of.
suspect so. Yeah, I haven't looked into it too carefully, but yes, because you have like a TITS building and a piecewise linear map, and I mean, yeah,
Right.
I mean, all the ingredients are there. There's no reason it shouldn't work, but that I just haven't done.
Yeah. Other questions?
Well, for reductive groups, maybe you want to be a tiny
Sorry.
bit careful.
So are there notion of forms and connections as well?
Could you please repeat the question or speak up?
So I'm saying, can you hear me?
Yeah, now I can. Yeah.
I'm saying, since you talked about dual bundles and so on, so are there notion of forms and connections as well?
I mean, harmonic forms exist to some extent. I mean, one forms and two forms and so on. Connections, in fact, we just 2 days ago, we discussed what a connection could be, and it turns out to be somehow almost the same thing as a harmonic form here, because sort of our situation is locally very much abelian, and then it's sort of a direct sum of harmonic one forms. And okay. You can come up with such a notion. I'm not sure you're going to be happy with it. Let's phrase it like that.
Oh, yeah.
So that's related to another question I wanted to ask you that, you talked about Narasimhan-Seshadri theorem.
Yeah.
So, you could have like, and then I asked you about Higgs bundles. So you have the Kobayashi-Hitchin correspondence and Nordström-Lenzing-Beckau theorem. So, I was wondering what would be the sort of PDE side of the story. Like you'd like to have a Hermitian-Yang-Mills equation.
Yeah, that's a very interesting question. And now I have to just claim ignorance. I do not know the PDE side of the story very well. I mean, the only thing I can say maybe is sort of that somehow the fact that some form of piecewise linear map, and maybe sometimes you want to impose harmonicity to a Brouwer-Titz building showing up, does remind me of some articles by Simpson and others. I think also including you actually as an author. I just have to confess my ignorance that I cannot make this precise yet. It just reminds me of developments there. That's pretty much it.
Thank you. That's it. Other questions? Comments? I had one more question. So you mentioned Atiyah's theorem.
Yeah.
On classification of vector bundles.
Yes.
So is the proof similar to the, in strategy to the proof of Atiyah, or?
Oh, it's much simpler, interestingly. The proof goes via this this proposition here, meaning that, well, in order to classify vector bundles of rank n, you need to classify covers of degree n. And covers of S1, you have fully classified by its fundamental group. So the proof here is much simpler. I mean, this I think the takeaway. But the statement is exactly in analogy with Atiyah's theory.
I see. Other questions, comments, or remarks? Online participants, please just unmute yourself and ask the question or type in the chat box. Other questions? So maybe on, I have one more thing. I guess you said, I was asking this question about the category of vector bundles, and you said that the morphisms aren't the right ones that, at least if you take the morphisms that come from F1.
I mean, there certainly are all morphisms. Maybe that's the way to say. I just think there should be more.
There should be more morphisms.
Yes.
So what would be like some of the features that you would want from the right category of morphism? I mean, the right category. See,
another way to describe morphisms, I mean, in some form of, I mean, maybe just let's assume we are working over the trivial metric graph, because that's already difficult. So you have like only the trivial vector bundle on it, and you want to have a homomorphism from a trivial vector bundle to a trivial vector bundle. So that's the same thing as a linear map from T to the N to T to the M. And somehow sort of the F1 geometric notion definitely gives you correct things, but I think there should be more. Namely, another way to think about it is you can take the product of Tn cross T to the M and take an element in the in the tropical Grassmannian of n-dimensional linear subspaces of t to the n times m. So meaning a thing that generalizes the graph of your linear map. And that type of object is in general a matroid or an evaluated matroid in t to the n cross m, and or the Bergman fan of a matroid. And there's sort of there's a whole lot of interesting combinatorics and tropical geometry hidden in that notion, and that just doesn't come from the F1 geometric notions in the naive way that we have been using it in this talk. So I think there should be more to be said, but I think the point is that one should first say what the best possible notion of a linear map is, and then we can say what a homomorphism of vector bundles is.
I see. Right.
Yeah.
Thanks a lot.
Yeah, you're welcome.
Any final questions or comments? Online participants or people here? If not, let's thank Martin again for a very nice talk.
Yeah, thanks for having me. Thanks for listening. And thanks for the applause that I cannot hear but see.
Sorry?
Sorry, it's funny to see that people are applauding that I cannot hear it. I can just see it. Anyway.
You cannot hear it.
I cannot hear the applause, but I can see people applauding.
I see.
Yeah.
Thanks a lot, Martin.
Yeah, you're welcome.